My name's Scott Power. I'm the Director of the Centre for Applied Climate Sciences at the University of Southern Queensland. And the Centre for Applied Climate Sciences has about approximately 20 staff, most of whom are in southeast Queensland in Australia. But we also have additional staff at the Bureau of Meteorology in Melbourne and also at the UK Met Office in England. And the centre primarily focuses on research, extension, monitoring and evaluation. And we also facilitate adoption to help people manage some of the risks they face from climate variability and climate change, and also to help them seize any associated opportunities. And in addition to those staff, we also employ a network of part-time staff embedded in community and industry called Climate Mates. And about 10 of them across Northern Australia, and they act as champions in the use of meteorological and climate science. And they help other people in their networks use that information in their decision making. And in addition to the staff, we have approximately 20 PhD and MSc students, most of whom are in Australia, but we also have some in Southeast Asia. And before I introduce our speaker this morning, I'd like to, on behalf of the Centre for Applied Climate Sciences, acknowledge the traditional owners on the land on which we gather. And I'd also, again, on behalf of the Centre, pay our respects to elders past, present and emerging. And it's my great pleasure to introduce my friend and long-term colleague and associate, Dr. Vikram Mehta. And Vikram is the Executive Director and the founder of the Centre for Research on the Changing Earth System. And that's based in Maryland in the USA. And this Centre for Research on the Changing Earth System specialises in the physics of decadal climate variability, its predictability, and its impacts right around the world. And so, as I said, it's my great pleasure to have known Vikram for many, many years. And I know that he has very extensive and profound experience in applications-orientated scientific research. And very brief bio, he started studying in India and then went to Canada. And he has an MSc and a PhD in meteorology from Florida State University in the US. And he then worked for many years as a research scientist, that's where I met him, at NASA Goddard Space Flight Center. And he further specializing in decadal climate variability. And then he founded, as I mentioned, the Centre for Research on the Changing Earth System in 2002. And this centre is a non-profit scientific research organisation, and it specialises in the physics of decadal climate variability, its predictability, and the impacts around the world on water resources and agriculture, as I mentioned. And also, just you might be interested in learning a bit more about what Vikram's going to be talking about today. He's published books on the topic. That includes things like natural decadal variability, its impacts, its mechanisms, and the degree to which it can be predicted. And in this seminar, Vikram's going to outline some of that great research that he's done over many, many years, over decades, in fact, linked to decadal climate variability. And after Vikram speaks, we're aiming to have a short Q&A session. So if you have any Q&A, any questions or comments, please put them into the Q&A facility. And then Louis will be hosting the Q&A session later on. So with that, I'd like to welcome Vikram. And when you're ready, please share your screen. Thanks very much, Vikram.
Okay, so can everybody see my screen?
Yep, we can see it. Thanks, Vikram. And we can hear you clearly.
Okay, so now it's in the full screen mode. Well, first of all, Scott, thank you so much for inviting me to give this seminar and renewing our acquaintance, collaboration, friendship, shared interests going back, I would say, more than 25 years. Okay, so it's really a pleasure for me to give this seminar in your center. And again, thanks also to Will for making all the technical arrangements and for putting this whole thing together. So as Scott said, I've been working on decadal climate variability, its impacts for more than 30 years now. in the last 20 years in the center that I founded, CRCS, as Scott mentioned. So I'm going to give today a very sort of large scale overview of the field, if you will, starting from decadal climate variability, its importance, its impacts on worldwide, water, crop productions, and other sectors. And then I'm going to talk about the socioeconomic consequences of these impacts in the Middle East and North Africa and West Africa, and then launch into something that I've been working on for some time, which is DCV adaptation science. So essentially addressing why, what, and how, and then summarize at the end. And I'll be very happy to answer questions, get into discussions, as well as if somebody is interested, I can send the PDF of my talk. And as Scott said, it's going to be recorded there anyway, so you can share the recording with other people. So as I said, some of my slides are very busy, so to speak, a lot of details, but I'm going to try and skim up over the large scale, and then you can look at the details at your convenience, and I'll be very happy to respond to email questions and so on also. Okay, so decadal climate variability and climate change, important for the next about 20, 30 years, more so as I will describe. So first of all, what is variability and what is change? So the upper time series here, upper figure, shows the temperature of the West Pacific warm pool going back to 1900. And the average has been subtracted from this. So you can see that.
Oh, sorry, Vikram, to interrupt. We can still just see your first slide.
This is the first. Second.
It's still on your title slide.
Huh. Sharing is paused. Still there?
Yep, I can hear you. Will, do we need to do anything at our end, or?
No, it says, okay, hold on. Says resume sharing, which I am doing, but it's not doing anything.
We can still see your screen. So the sharing seems to be working. It's just not moving to the next slide.
Okay, let me stop and then go back again. See if I can. Okay now?
Yep, we can see just the title, Climate Variability and Climate Change.
Right. You can see the...
Now I can see the time series, thanks.
Okay, good. Sorry about that. Okay, so the upper time series shows just the anomaly in sea surface temperature of the West Pacific warm pool going back to 1900. And the average has been subtracted. So the first thing that jumps out is this increasing or warming trend, as you can see from beginning to end. Okay, so if you subtract the trend, then what you get is the bottom time series. So if you fit a linear trend to this time series, then what you get is the bottom, and there you can see the variability very clearly. And you can see decadal or even longer time scale variability in this time series. So I just wanted to sort of show what I mean by change and what I mean by variability. Okay, so now that is the past. So future climate variability and climate change. So climate variability has been occurring for millions of years at a variety of timescales. Now we know that climate is also changing due to human influences. But in our lifetimes, most of us will be much more affected by decadal climate variability than by human influenced climate change. And now IPCC reports have also noted this fact. For example, from the last major report which came out, AR6, which came out in 2021, the point C1 mentions that both natural drivers and internal variability will modulate the human caused changes, especially at regional scales and in the near term. And by near term, they mean the next 20 to 30 years. They also go on to say that these modulations are important to consider in planning for the full range of possible changes. So they are now acknowledging that natural variability is certainly very, very important. And then in the next or subsection of the same section, they talk about how the global average surface temperature has been impacted by internal decadal variability and so on. And I'll show an example of that in my talk. And then another paragraph or another point talks about the importance of internal variability, especially in the near term, certainly at global scales, but more so at regional scales, especially in monsoonal regions. So they expect that IPCC expects that the near-term changes will be dominated by effects of internal variability. So that is why it is very important to study, predict, and try to adapt to this internal variability. So what is decadal climate variability? The history goes back several centuries, started with sunspot cycles. Now we are talking more about the physics of this variability and so on. But these are essentially climate cycles, so to speak, with 8 to 20-year periods. And we can see them in a very variety of different kinds of data on oceans, land, atmosphere, and so on. The main causes, as far as we know today, are ocean-atmosphere interactions, land-atmosphere interactions, stratosphere, troposphere, ocean interactions, and solar variability, certainly. On the right, I have listed a variety of DCV phenomena, or the major DCV phenomena. Interdecadal Pacific Oscillation (IPO), it's also named, also known as Pacific Decadal Oscillation or PDO. Tropical Atlantic SST gradient variability, West Pacific warm pool oscillation, and so on, or decadal variability of ENSO. So just to show a couple of major decadal variability examples, this is the so-called Interdecadal Pacific Oscillation, or IPO. And I had the good fortune to work with Scott and Chris Poland and other people on this, the first paper on IPO, which came out in 1999. On the left is the sea surface temperature anomaly pattern, which shows in the positive or warm phase of the IPO, much of the tropical, subtropical Pacific is filled with above average temperature water, and then the opposite sign in the mid latitudes. And the time series on the right show a variety of IPO indices, and you can see decadal, multi-decadal variability. So this was the beginning of our collaboration. We did actually set out to discover the IPO. If I remember correctly, we started wondering about what was modulating the relationship between the Southern Oscillation Index and wheat prices or wheat crop in Australia. And then we found that the correlations sort of varied at decadal, multi-decadal timescales. And then, so in that process, accidentally or serendipitously, we discovered the IPO. And its namesake, or not namesake, but the same phenomenon, but known by the name Pacific Decadal Oscillation, or PDO, was also discovered not by people looking for climate variability, but Mantua and company in University of Washington at about the same time when we were looking at, when we found the IPO, they were looking at what modulated the fish catch in the North Pacific Ocean. And they found sea surface temperature variability, which correlated very well with the fish catch. And they named that variability the Pacific Decadal Oscillation. But as this figure from Ben Henley's 2017 paper shows, the patterns are more or less the same, IPO, TDO, South Pacific Decadal Oscillation, or decadal variability of Nino. And the right-hand side shows the time series, IPO index, PDO index, etc. You can see that they are all more or less the same. And so I think I would just call them the same phenomenon, essentially. The second one I would like to introduce is the decadal variability of sea surface temperature oscillations in the tropical Atlantic. And the map on the right shows sea surface temperature anomalies on essentially on two sides of the equator. So blue is cold and red is warm. And so this is pattern. This is a pattern when the tropical Atlantic gradient or tag index is positive, and then it flips sign when it's negative. And you can see the time series going back to 1900. Even without doing any spectrum analysis, you can see that it has both, certainly some interannual variability, but mostly decadal, multi-decadal variability. And the spectra at the bottom show they are calculated for annual SST data as well as seasonal SST data, as you can see. As you can see very well, there is a very strong, the strongest peaks are at about 10 to 14-year periods, and then also somewhat longer time scales, 20 to 50-year period. So this is the second phenomenon that I wanted to introduce. The third one, which is important for Australia, is the so-called SAM, or the Southern Annular Mode, which is the pattern of sea level pressure and winds, essentially, in subtropical to polar latitudes in the southern hemisphere. But what these people found, Yuan and Yonekura, is also that there is a very distinct sea surface temperature signal also associated with this decadal variability of SAM. So the upper left-hand figure shows the spectrum of the SAM index, and you can see very strong peak at decadal timescale. And then there are these three other boxes, which are spectra of SST anomalies in three 10-degree wide latitude boxes. And you can see all of them have this decadal peak. And there is quite a bit of work done about what causes all of these decadal, multi-decadal phenomena, PDO, IPO, PDO, the tropical Atlantic variability, SAM, also its counterpart in the Northern Hemisphere called the Northern Annular Mode or the North Atlantic Oscillation, and West Pacific warm pool variability as well. So I will very briefly touch upon the physics or the hypothesized mechanisms next. There are several proposed hypotheses. The oldest is integration of atmospheric noise by ocean's thermal and mechanical inertias. And this integrated noise essentially manifests itself as low frequency variability, including decadal and longer timescale variability. So that is the oldest proposed mechanism. Others are interactions between meridional vertical ocean circulations and atmosphere, slow propagation of off-equatorial oceanic Rossby waves and their interactions with features in the ocean as well as in the atmosphere. Then, as I mentioned, the history of this field goes back at least a couple of centuries, maybe even longer, in which solar influence was invoked to understand, explain, predict climate variability. But now, in the last 30 years or so, with satellite-based observations of solar irradiance, spectral irradiance of the sun from satellites, and also climate models, which can sort of simulate the present-day climate more realistically. All of these have combined to come out with hypothesis of two possible solar mechanisms. One is called the so-called top-down mechanism, which is the solar ultraviolet radiation acting on stratospheric ozone and dynamics, and then this effect then works its way down into the troposphere and down to the ocean surface. And another one is called the bottom-up mechanism, in which solar visible radiation stimulates unstable interactions between tropical, subtropical ocean and the atmosphere. And the two together can come together and produce a very substantial response, as the most recent modeling work is showing. And so the solar variability may be acting as the pacemaker or as a pacemaker of decadal variability. And then this can start from the tropical Pacific. And since other oceans, tropical oceans are connected to the Pacific via water circulation teleconnections, and they also have some local unstable ocean atmosphere interactions. So they also could be playing a role in this. So these are some of the major hypothesized mechanisms of decadal variability. In terms of decadal climate predictability, where are we? Now, this is a very difficult problem because it is at the overlap of initial value problem and boundary value problems. Boundary value problem because constituents of the atmosphere in terms of greenhouse gases, in terms of volcanic material, solar radiation, they are all important as we go towards longer timescales. And this happens to be the time scale, decadal happens to be the time scale where an initial value problem and boundary value problem, they overlap. Therefore, even estimating decadal climate predictability is very difficult. And then there are other limitations as I have listed here. But empirical and dynamical methods are being developed to estimate predictability and to actually make predictions. These estimates and predictions are still very much in their infancy, but they are encouraging, and they are limited mostly to surface temperature and sea level pressure. These efforts, they have to go a long way before they can be useful, but WMO has recognized the importance of decadal prediction, and therefore they have organized a so-called Grand Challenge on near-term climate prediction with the UKMO Hadley Center acting as the lead center for this prediction. However, for students, for young postdocs, this is an open and very critical area of research. So if you are looking for a problem to work on, this is a very important one and a very interesting one as well. Okay, so what are the worldwide impacts as far as we know today? Again, I'm going to skip over details, show only the major aspects of it. So here on the upper row shows empirical orthogonal function analysis of Palmer Drought Severity Index, which is an index of dryness, wetness, if you will. It's also used for droughts, for defining droughts or declaring droughts and so on. That's why it is named the Palmer Drought Severity Index. So the figure on the right shows the global map of this first empirical orthogonal function of PDSI using data from 1961 to 2010, so 50 years of data. The blue is wet, where the index is PDSI is positive, red is dry, or dry, where the PDSI is negative, as the scale here at the bottom shows. The associated principal component time series is shown on the left with this black line. And what is overlaid is the PDO index in red and blue, again, going back to 1961. So you can see that the PDO or IPO seems to be, in some way responsible for causing these worldwide decadal hydrologic cycles. You can see very large areas of the Earth. In one phase of the cycle, they experience dryness. In the opposite phase, they experience wetness. The correlation between the PDO or the IPO index and the PDSI principal component, that correlation is 0.77. This is without any filtering, okay, only using annual data. So you can see how strong a modulation of the global dryness, wetness is caused by IPO or the PDO. And the bottom row shows something similar, but in a different way for the association between tropical Atlantic variability and dryness, wetness around the world. Now, if you want to look at other things besides just the dryness, wetness, the data are not very easy to come by. There is something called the Global Runoff Data Center in Germany, where all countries are supposed to send their runoff data or river flow data, but very few countries actually do that. As you can see from this map, there are very large areas of the world which do not send data to GRDC. US certainly is very well covered, as are Western and Northern Europe, Southern Africa, some parts of the Atlantic seaboard in Brazil and Argentina and so on, and Eastern Australia, some of Northwestern Australia as well, and also New Zealand. So what this shows is the first empirical orthogonal function, which explains about 40% of the variance, again, going back to 1961. So 1,850 locations around the world. The correlation of the principal component with PDO is 0.36, and with the tropical Atlantic is minus 0.48. And on the right, I have listed the difference or the change in river flows for individual major rivers between the positive and negative phases, or the positive maximum and the negative minimum of, let's say, the PDO. So for example, in the Mississippi River, many locations experience as much as 50% change in river flow, going from positive phase of the PDO to negative phase of the PDO. And so on in other parts of the world. As you can see at the bottom is the Murray River in Australia. It has a very high correlation with West Pacific warm pool variability also. And I have looked at the physical consistency among implied atmospheric water vapor transport, precip, PDSI, and river flows, and DCV phenomena, and they are all physically consistent. So it looks like, again, as I showed in the previous case of the PDSI, causing this very large dryness, wetness oscillations around the world, it looks like river flows also experience this effect of DCV very sort of noticeably from where the data are available. Then the next is crops, and the story is nearly the same, not as bad as for river flows, but nearly the same as that countries are supposed to report their crop productions every year to the UN's Food and Agriculture Organization. Most of them report only one number per crop per year. So you have just one number, and for very large countries such as Brazil or China or India, Australia, you have just one number for each crop for the entire country per year. And so the analysis is extremely difficult. However, we examine 400 crop country combinations, so 20 countries and 20 crops in each country. These are all available, data are available freely from the FAO. And what I am showing here, just a representative sample of results, is the change, again, like the river flows, the change in, this is the percent change in crop production between positive and negative IPO phases. Okay, so you can see in the US, for example, wheat, 15%, barley, 20%, avocado, 35%. And for Brazil also, you can see some of the staple crops, very large differences in crop production. In subsistence farming countries in Africa, this is particularly bad because these are all their staple foods, and they are very substantially impacted by DCV phenomena. But not just in Africa, also, for example, Middle East, even in France, India, China, Australia, biggest change is tree nuts, and I will come to this in a minute, grapes, sorghum, and so on. So now let's focus on Australia. So the left-hand column of two columns shows the correlation coefficient between average DCV indices and detrended river flow anomalies. Again, this is GRDC data from 1961 to 2010. here, the left-hand column is for December, January, February, which is the Australian summer, also New Zealand summer, and June, July, August on the right, which is the winter in the Southern Hemisphere. The top panel is PDO, then Tropical Atlantic, West Pacific Whirlpool, and Nino 3.4. So you can see that the correlation between, and the filled boxes show correlations which are significant at 95%. So you can see along the East Australian coast, the correlation between PDO and river flow anomalies is substantially high, 0.4 or even higher in DJF, and somewhat weaker in the Australian winter. Similarly, West Pacific Whirlpool, you have some in JJA, this is the winter time in Australia, and then Nino, both in Australia, also in New Zealand, in both DJF as well as in June, July, August. On the right are composite anomalies expressed as percent of seasonal average for PDO positive average, average positive value of the PDO index on the left, average negative value of the PDO index on the right. And what is plotted are composite anomalies as percent of seasonal average. So this is DJF and PDO positive, for example. So in Australia, okay, so in Australia, I'm sorry about that. In Australia, the change is about 20 to 30% of the December, January, February river flows all along the Australian east coast. In June, July, August is not as much, and actually some of that is positive here. In December, January, February, it is negative. In the negative phase of the PDO, it is positive, meaning there is more or stronger river flow, more water flowing in the rivers along the east coast here, and so on and so forth. And there is some association with tropical Atlantic as well. Looking at Australian crops in detail, the table here shows various crops, major crops, and their correlations with IPO, West Pacific Whirlpool, tropical Atlantic, Nino, etc. And I have highlighted some of them in the table with bold fonts: sorghum in June, July, August, oats, oranges, mango, grapes, tree nuts, and so on. And the map shows where these crops are mainly grown in Australia. Sorghum, for example, you can see sorghum production in March, April, May, Nino. The correlation coefficient is minus 0.61. And you can see the anomaly in production is also quite large compared to the total or the average, which is 1.2 million tons. The anomalies can be as large as 0.5, 0.6, so about 40 to 50%. Similarly, Australian tree nut production and PDO, very highly correlated, minus 0.72 is the correlation, with again, very substantial anomalies compared to the average. So as you can see, when wherever there are data available, you find impacts of decadal climate variability, with the IPO, PDO making the maximum impact. But in Australia, in Africa and in South America, the tropical Atlantic variability seems to be making as large an impact as the IPO, PDO. So if we look at now the impact on socioeconomic and political conditions in the Middle East, I have three countries here: Iran, Syria, and Saudi Arabia. And what is plotted is the wheat production anomaly. The solid line is the wheat production anomaly in each country. The dashed line is the wheat import anomaly for each country. Okay, and the total or the average is here, as is the production average. So the 50-year average annual wheat production in these three countries, Iran, Syria, and Saudi Arabia, is about 13 million tons. the aggregate production difference between PDO phases, this is the PDO index. So the aggregate production difference among these total of these three countries is about 5 million tons between PDO phases. So that is very substantial fraction of the average production. So PDO causes marginal security of major staple foods. Wheat and barley also has similar looking figures. So both, they are two staple grains in these countries, and both are impacted by PDO quite substantially. Now, another twist to this story of the Middle Eastern countries is that Russia and Ukraine are the main sources of wheat for these and other Middle Eastern countries. When beginning in about 2006 or so, as you can see, the PDO went south or negative. The wheat production also went negative, as you can see in Iran, here, Syria, Saudi Arabia. Their usual sources of supply, Russia and Ukraine, dried up because they were also suffering from production problems. And so they put a partial embargo on exports. And so these countries received much less wheat and barley than what they wanted to because of their own production shortfall. And that certainly gave rise to, or was a catalyst for the so-called Arab Spring beginning in about 2010-11, certainly in Syria. You can see how there was a precipitous decline in wheat production from about 2002-3 all the way down to 2014-15. So that certainly acted as a catalyst of socioeconomic and political unrest in the Middle Eastern countries. Here this shows PDO index and Palmer drought severity index. Again, very high correlation between the two. As you can see, these are smooth, and you can see very high correlations. So that as you can see here, there are dry epochs during negative PDO phases. You can see here and here. Droughts cause water and food insecurities and consequently political instability. In Mali also, their agriculture is mostly subsistence based. Same sort of problems. Their tropical Atlantic seems to be playing a much bigger role. As you can see, very high correlation between tropical Atlantic gradient variability and the PDSI. Again, dry epochs in these negative tag phases, they cause water and food insecurities and catalyze instability and armed conflict. Somewhat similar story, or even worse story, in Burkina Faso, also in West Africa. Their PDO seems to make a big impact, not only on food crops, but also on forage crops, so that the PDO correlations with numbers of draft animals and livestock substantially high. And they cause serious consequences for impacts on livestock for pastoral people, and they have violent conflicts with farmers as a result of all of this. And as you can see, negative correlations with PDO with all their staple crops here in Burkina Faso. Same story about Nigeria also, is just that the list of crops affected much longer than in Burkina Faso. Same sort of consequences on livestock, and then socioeconomic and political strife, conflicts between pastoral people and farmers, and so on. Okay, so this is to give you an overview or a flavor of how, or the association between DCV phenomena and water, food, etc., and how those impacts lead to socioeconomic and political conflicts in some of these countries that I talked about. So certainly, as you can see, it is very important to understand and predict decadal climate variability and its impacts. Last but not the least, it's also very important for attributing global climate change. And what this shows is from a paper by Ben Henley and King in 2017, and they estimated the impact of IPO phases on attributing or on verifying the Paris Convention target of 1.5 degrees C warming compared to the 1850 to 1900 baseline. And so this is the observed global mean surface temperature. Anomaly is meandering along, but also warming, as you can see. And it would go right through here like this if there was no IPO. But because there is IPO, there are two possibilities. If the IPO is in the positive phase, and because such a large amount of the Earth's surface is covered by warmer water, warmer surface water during the positive phase of the IPO, it has a major projection on the global mean surface temperature. So if the IPO is positive, this would be the trajectory of the global mean surface temperature. So it would cross the 1.5 degree Paris target maybe in 2026, halfway through 2026. However, if the IPO is in negative phase, it would not cross that target until maybe about halfway through 2031. So depending on where is the IPO, there can be as much as a 5-year difference or uncertainty in whether or not the global mean surface temperature has exceeded the Paris target. So it has a huge impact on attribution and also on monitoring whether or not this target has been met or when, or and so on and so forth. And incidentally, my group has been making decadal dryness, wetness outlooks for the last about 3 years. And as a part of that, we make statistical outlooks of IPO index and tropical Atlantic and so on. And we put out an outlook which last year, which said that we expect, based on the past data, statistical, probabilistic statistical outlook said that the IPO would be approximately positive in about 2024-25 timeframe. So just about here. Right now, the IPO has been in the negative phase for the last 3-4 years. Just now, as a matter of fact, this year, it is the coldest it has been since about 2012. Okay. However, our projection is that it will come out of this negative phase into the positive phase sometime 2024, 25, and then maybe grow to a fairly sizable amplitude. It just so happens that today, Hadley Center put out a report saying that based on a number of decadal forecasts that they have made, their projection is also that this point will be reached sometime in 2024-25 or so. So it shows that certainly IPO has impacts on the world in and of itself, but also for matters such as verifying these kinds of targets and so on. IPO phase and amplitude play very important roles. Okay, so adaptation. Let's quickly go over to adaptation. I have about 15 minutes, so I will be really speeding through this. What is adaptation? It is the adjustment of organisms to their environment in order to improve their chances at survival. Okay. Okay, this shows based on tree rings, Palmer Drought Severity Index calibrated from tree rings in North America going back to 1006 current era. Okay, so so this is 1000 years. And I have marked periods of extreme dryness and extreme wetness by red and blue boxes, as you can see here. And beginning in early 19th century, when records started being kept in North America, I collected those records and associated these dry and wet epochs with what happened during those times. And as you can see, alternately dry and wet epochs associated with the development so to speak, of North America, the growth of the US west of the Mississippi River, crop failures, large-scale migrations, and so on and so forth. And this has been continuing all the way till today. But in other records, which go back way back, all the way back to maybe about 1200, 1300 AD, it seems that these alternate dry and wet epochs caused the rises and falls of Mississippian and other civilizations in North America, going back to about 12th, 13th century or so on. A similar story of India based on tree rings, PDSI, and here also the red boxes are prolonged periods of dryness or droughts, which cause famines. As you can see, other literature shows that millions of people died in some of these famines or droughts which cause famines. All the way to the modern times, the last such big famine was in the 1940s. Since then, there have been droughts, but no such large-scale deaths, but hundreds of millions of people have been affected. If you look at tree ring-based PDO index or IPO index based on coral delta oxygen 18 isotope data, then what we can see is that if we compare the PDO indices and the IPO index with these tree ring-based PDSI data, what they show is that in the last about 300 years or so, there have been 6 dry epochs in North America, which were associated with the negative PDO phase, and 7 wet epochs, which occurred during the positive PDO phase. And instrument data and model, climate model simulation show that where the the PDO is negative, as I showed with data, there are dry epochs in North America, and when it's positive, there are wet epochs. So it looks like the PDO or the IPO has caused decadal hydrologic cycles in North America, monsoon Asia, and elsewhere for at least the last 300 years. So what have we learned? That there are these prominent hydrologic cycle periods indicating nearly cyclic mega droughts and pluvials in the last 1,000 years may have given rise to rises and falls of civilizations, even struck death blows to some of them, catalyzed revolutions and mass migrations in Europe, and caused famines, millions of deaths, mass migrations, and political awakening in India. So essentially what we have seen is that alternating wet and dry epochs have witnessed human migration surges, development of agriculture in cities, but when the dry epoch came, crop failures, water shortages, large-scale economics, and suffering, and so on. So what have we learned? As George Santayana said, those who cannot learn from history are doomed to repeat it. And it looks like we have been repeating this over and over again for at least the last 1,000 years. But then, as Aldous Huxley said, that men do not learn very much from the lessons of history is perhaps the most important of all lessons of history. So can we learn now? That is what adaptation should be all about. I wanted to show this very quickly, but I would rather go direct more to, okay, so what this shows is our work on simulating impacts of decadal climate variability in the US, mainly in the Missouri River Basin, which is the largest river basin in the US. It is a breadbasket not only of the US, but also of the world, produces more than 40% of the wheat, more than 20% of grain, corn, and about 1/3 of the cattle in the US, this area. The total value of crops and livestock is over 100 billion per year. Okay, much of the cropland is non-irrigated, so it's dry land, so to speak, dry land agriculture. And there are also thousands of urban areas of various sizes, industries, and so on and so forth. So there is competing demand for water among a variety of sectors. So we have simulated impacts of decadal variability on let's say here, wheat production. So the upper figure shows observed data from the National Agricultural Statistical Service during a wet epoch and our simulation using SWOT model, soil and water assessment. So during a wet period, as you can see, it's dryland agriculture or non-irrigated agriculture produces very high or higher wheat yields, as shown also by observed data or estimated data. And during dry epochs, you can see the model simulates less or lower wheat yields, and that's confirmed also by observed data. This shows the impact of various DCV combinations of phases. So positive PDO, negative tag, and positive worm pool produces this pattern of changes in spring wheat. Then when the phases change, opposite phases, then you get opposite. So red is below average production, blue is below average wheat yield, and blue is above average wheat yield. And here in winter wheat, PDO plus, tag minus, and so on, you have above average wheat yields in the southern part of the basin and below average in the northern part, and then it flips when you have the opposite phases. So we are pretty confident that we are capturing here, the model is capturing the impacts of DCV phenomena. Okay, simultaneously with data analysis and modeling work, we have also been interacting very closely with stakeholders going back to 2006. And we have had extensive and intensive discussions with over 200 stakeholders, farmers, water management managers, government officials, commodity shippers, NGOs, academics, and other stakeholders via many workshops, webinars, individual discussions, and so on. What they have told us is that DCV impacts are qualitatively and quantitatively different from those associated with seasonal to interannual climate variability. And there are substantial impacts of decadal dry or wet spells on a variety of societal sectors, urban water systems, crop production, as I showed, hay and grass production, livestock, infrastructure, so on and so forth. So they, according to stakeholders, there would be benefits for planning in all sectors if we can produce decadal climate outlooks. Even if we can just produce the current state or nowcast of DCV phenomena, then they can perhaps use it to their benefit. It would be also potentially very useful in guiding a broad range of short and long-term decision making, and also as an educational tool to foster awareness of inevitability of future variability and extreme events, and help in justifying proactive management and associated expenditures. Okay, so for individual sectors, these are a variety of ways decadal climate outlooks can help farmers. A variety of ways here they can help in wildfire control. A variety of ways in which decadal climate outlooks can help in river flow and reservoir sectors, as you can see. And but then it's not all rosy. I mean, there are potential barriers to using these decadal climate outlooks because first and foremost is that the credibility of decadal climate outlooks is not yet established by forecasts of past DCV and its impacts. Also, better understanding of institutional rules and regulation, laws, other legal matters are required because they pose barriers. And better understanding of how decisions are made by individual farmers, dam operators, government officials, etc., politicians, financial institutions, and others, that is required. Also, there is a need for a safety net for stakeholders who are willing or interested in applying these DCOs in decision making. Just as we need to inform the stakeholders, we also need to be informed by the stakeholders about what their needs are, about the terminology that use, about what their concerns are. In many cases, we found that weather and climate information does not play a role in decision making. There are other things, for example, because now the grain trade is globalized. So um, what are the prices or likely prices of soybean in Brazil or in China, or wheat prices in India? Those have much bigger impacts on the farmers' decisions in the US compared to what are the climatic conditions likely to be next year or in the next 2 years and so on. Also, there is need for cost benefit analysis of applying these decadal climate outlooks in individual sectors, so that people can see sort of in dollars and cent terms what are the benefits. So we did one such study in the Missouri River Basin to adapt crop choice and land and water use to DCV and impacts information. Then this is the paper. If anybody is interested, you can go into that. We used um, I worked with a very well-known agricultural economist, Bruce McCarroll, in Texas A&M University, and his students. We used a stochastic mathematical programming model.
Oh, sorry, Vikram, your microphone stopped working.
Mine? It.
We're just about out of time too, so we might have to get to your conclusions pretty quick if you wouldn't mind.
I think that's what I will do, because you can look
We
at
still
this.
can't hear you.
Yeah, in your own time, you all can look at this. So I want to go to my.
We're not hearing you, Vikram.
Oh,
you're not muted, but we can't hear you, so I'm not quite sure what's happening.
Yeah, I don't know because.
I can hear you now.
Can you hear me now?
Yeah. Thank you.
Okay. So I will not go through all of this, but just show a couple of things. So we went through a number of optimization exercises and so on, and we found that, yeah, certainly decadal climate variability information, just the phases can make a big impact on the agricultural economy of the Missouri Basin. Even if we have just conditional forecast, there would be net benefits of about $30 million annually. Perfect forecast would yield net benefits of up to about $80 million annually. And recently, this has been extended to the entire US's agriculture enterprise by Bruce and his student. And they found that with perfect forecast of DCV for next year, the net benefits to US agriculture could be of the order of $1 billion annually. Okay. So you can see how important this information can be. Okay, so I would like to talk about this last thing, elements of DCV adaptation science, based on our experiences that I described, and much of this we have already published. So the first question is, adaptation to what? Climate is not the only driver of societal sectors. So there are other drivers such as population changes, consumption pattern changes, and so on and so forth. They also act at multi-year to decadal and longer timescales. All these drivers must be included in developing adaptation options. Secondly, adaptation for whom? There is competition among countries, regions, sectors, people, both producers and consumers, and institutions for resources, products, material prosperity, and other benefits or advantages. So how and for whom to optimize adaptation options? Now, one thing that I would like to make very clear is that adaptation to DCV is not the same as adaptation to climate change, because in the case of DCV, it's a natural phenomenon, so no mitigation is possible. Only adaptation is possible. We have no control over nature, so we just have to adapt to whatever nature does. Secondly, DCV does not make unidirectional impacts. DCV impacts are cyclic, so they have to be taken into account in developing adaptation. As I showed, societal impacts of past DCV are documented. So how societies responded or adapted in the past can be studied to develop insights into decision-making processes. Finally, stakeholders say that decision horizons of 5 to 10 years are actionable. Beyond that, they don't think that any information can be really be useful for taking any kind of action. So these 4 points make it very clear that DCV adaptation is not the same as climate change adaptation. So now, what are the elements? I define adaptation science as the sum of science for adaptation and science of adaptation. So what is science for adaptation? So that is fundamental DCV science and the associated climate science. So interactions between DCV and all the way down to daily weather. Secondly, decadal climate and weather statistics, predictability estimates, and probabilistic prediction. This would also be science for adaptation. Development of models, methodologies, and scenarios, especially of these other drivers which I mentioned, for simulation and prediction of impacts. And then of using all of this analysis and modeling of impacts on various societal sectors. And then finally, societal impacts, predictability, and prediction. This would all be, according to me and according to what we have learned from stakeholders, this would be science that we have to do for adaptation or to inform adaptation. Science of adaptation would consist of analysis and modeling of decision-making processes and barriers in various sectors, estimates of value of DCV and impacts information, analysis of and modeling of intra-society benefits or losses due to adaptation, then impacts on intra and international trade flows, conflicts, etc., and development of interfaces with climate change adaptation. So to summarize, you can see, I'm sorry, I went over some of the things very quickly and tried to cover too many things, but I hope that I gave you a reasonably accurate and interesting overview of the entire field, including impacts and the evolving or the nascent field of DCV adaptation. So thank you very much. And these are the 2 books I wrote, and they were published by Taylor and Francis CRC Press. The impacts book was published in 2017 and the physics book in 2020. Here are our websites. You can go there and get some of these papers, certainly see what kind of work we have been doing. And at the bottom is my email address, so feel free to send me an email if you would like to know more or if you have any question or comment. Thank you very much. And Scott, I'm sorry I ran over time.
No worries at all, Vikram. Thanks very much for a great talk. It was fascinating to, well, also impressive, the breadth of it, but also some fascinating information there, particularly about the some of the profound impacts in the